right, folks, yes, it is section 4.6, inequalities for one triangle, and that means this is day number 2 because you've already done a night of homework of section 4.6, and we've also had one lesson on section 4.6, inequalities of one triangle, and we actually had kind of a lot there in that lesson. Remember, across from or opposite the smallest angle in a triangle is going to be the smallest side in a triangle. And across from the largest side of a triangle, for instance, or opposite the largest side, you get the largest angle of a triangle and whatnot. You can also determine what's the middle size by similar logic there. So we got those theorems. We also got those corollaries again, too. Remember, we measure distance by drawing in a perpendicular segment. That's nice. That's how we measure distance in geometry and in the world. Measure distance by drawing a perpendicular segment from a point to a line. But remember, the perpendicular segment from a point to a line, what was the fact we learned about it last class? We learned that the perpendicular distance from a point to a line is the shortest distance that you can find from a point to a line. And also from a point to a plane, it would be the perpendicular to the plane too. So we learned some important stuff. There was kind of a lot there. We learned properties of proportions as well. We learned properties of inequalities as well. Those 5 properties of inequalities, like transitive one, the multiplication property of inequality, the addition property of inequality. What else? The parts property and the substitution property of inequality. So guys, there was a ton there. There's just one more theorem, okay? There is one more theorem, which is part of the reason why we're doing a second day. But mainly, I just want to provide you a second day to get some practice. So what we're going to do today is we're going to spend about half of this time that we have together, half of it talking about the one remaining theorem, and it's a big one. This one remaining theorem's name is actually called, wait for it, the triangle inequality theorem. Yes, and that is a pretty well-known theorem throughout geometry. Not just in this textbook, pretty much any textbook is going to have this theorem, the triangle inequality theorem. And yes, it's a theorem that we can write about any triangle. So any triangle, we can apply this theorem, and it'll be some more information we can learn about the most important shape that's in geometry, triangles, of course. And to give you a little taste of what the triangle inequality theorem is here, perhaps you read this already as I've been blabbering on, I have down below a little bit of an example here. So it says here that the lengths of 2 sides of a triangle are 3 and 5. Then it says, after that, it says, don't give me the side length of the third and remaining side, right? Because you don't know that exactly. But the second sentence is the length of the third side must be greater than blank, but less than blank. So think about it, maybe sketch it out. But if you kind of understand what kind of a question this is asking and how you can maybe see if you can come up with an answer to this. Your first guess, your first inspection here, you have draw a side length of 3 tick marks on your graph paper and then another one of 5 tick marks and then play with them. Figure out what's the shortest the third side could possibly be. And then what's the longest that third side could possibly be? And that's going to give you an idea of what the triangle inequality theorem is. And we know that written out like this here, it's going to have something to do with inequalities, right? Because we see greater than and less than. Okay, so the triangle inequality theorem will have some sort of like in-between values that we kind of describe in order to figure out how long the sides can be given some information. All right, so without further ado, let's go ahead and jump on into it. I will see you guys on the other side. Section 4.6, day 2, inequalities from one triangle. I'm looking forward to this. Let's get it going. Triangle inequality theorem coming up right now. All right, and here we are to the other side of our little introduction here, section 4.6, day 2, theorem. We're diving right into it because I said it so much in our introduction. We're diving straight into the triangle inequality theorem. So we can tell you about that right now. And here we go. Theorem, the triangle inequality theorem. So this is going to be for any triangle. Any triangle, we're allowed to say this inequality statement here. Okay? So again, we're talking about the sums of the lengths of triangles here. So the sums of the lengths of any 2 sides of a triangle, it has to be greater than the length of the third side, greater than the length of the third side. Okay, so triangle inequality theorem. So far, we only see a greater than symbol. I said in the last slide, might be thinking of this in terms of greater than, less than. But if we really think about this one through, this just doesn't tell us what the largest, or sorry, like the two side lengths need to be larger than the third side. It also tells us that this third side and one of these two other sides here need to be larger than one of the original first two sides. Okay, anyways, that was super confusing. I'm gonna have to explain this one a little bit more. So anyways, just read it, write it down. Again, I'll give you 10, 15 seconds to write it down and really think about it. But this is a little bit more complicated than what meets the eye here. Okay, so the sum of the lengths of any two sides of a triangle, they have to be greater than the length of the third side. So let's go ahead and draw it on in right now. Okay, so maybe we can talk about it a little bit first. So say we have a side length of 3, for instance. A side length of 3, for instance. And we have a side length of 5, okay? We have a side length of 5. If I were to draw a triangle where a side length of 3 and side length of 5 were two of the sides of the triangle, what's the way that I can draw that triangle where the third side, the one that we don't know, right? We have this other hypothetical side, question mark, a way we can put these two sides together where a way whether this line can be as large as it possible is, because a side length of like this long would be super, super big. Okay, let's talk about it maybe over here. I'm gonna cross all this out here and just redraw over here. A segment of 3 and another side length of 5. If I drew the side length of 5 right here, my remaining side isn't very big. If I drew the side length of 5 right here, the remaining side's kind of small too. So if I move further and further away, right, further and further away, if I draw a side length of 5 right here, this would still be a triangle. So maybe this might demonstrate this pretty closely right here. So here I have a segment of 3, a segment of 5. Let's put them together. So now we have 1, 2, 3 non-collinear lines. So we have 2 of the sides of a potential triangle here. So question, what is the maximum size that this third side could be? Well, this is 3. This is 5. I tilted a little bit in here. So it's not 3 plus 5, right? 3 plus 5 would be 8. And that would be approximately this long, right? If we tilt this down here, okay? So it turns out, right, we would just, the third side here would need to be small enough, right? Small enough to not be over too far from 3 plus 5, right? 3 plus 5 needs to be greater than this third side so that you can actually go non-collinear, right? Not along the line itself, outside the line a bit, 3 units, and then 5 units back to where this final side is here, okay? So less than 8 is the largest that third side could be. Question, with the 3 and 5 segment, right? 3 and 5 segment, what's the smallest? What's the smallest the third side could potentially be? So let's test it out again here, at least like kind of inductively observe this a bit. Okay, if we had a side length of 3 on our triangle, how could we arrange the 5, side length of 5 in such a way where we can kind of guess perhaps what might be the minimum length, right? Minimum length for the third side. Let's check it out. Well, if I drew it over like this, we're going to end up with a really large triangle, really large obtuse triangle, right? And a really large third side, right? Third side up here. So the closer I draw it, right? So if I draw like this, the third side's still pretty big, not as big as this here, this 8. But if I draw it super close to the 3, maybe just slightly above the 3, the segment of length 3, right above this point. So I know it's going to go to a non-collinear point because it'll be just above that point right here. So this looks like this is about 5 units in length. If that were 3, then this is about 5. In order to complete a triangle, right, we have 3 non-collinear points, 1, 2, and 3. Those are 3 non-collinear points, right? These are collinear with one another. These are collinear with one another, but not all 3 are collinear. So I can form a triangle by drawing a third side. And guesses here, right? If this one on top were 5, this one on top were 5, and this one here were 3. What's the minimum size now? Minimum size now that this third and remaining final side would have to be. it would have to be greater than 2, right? Greater than 2. See, because if we go from this point to this point, the shortest way we can get between 2 points is by drawing a straight line, right? Drawing a straight line. So if we're going on a triangle, right, we're going on 2 different lines. If we're going on 2 different lines, that means we're taking a detour to a third point, right? To a third vertex of a triangle. So if this were 3, this side would have to be at least 2 because the sum of these 2 sides needs to be greater than the length of the third side in order to cover it, right? In order to create a triangle, okay? So in this situation, if I have 2 sides, length of one with the length of 3 and one with the length of 5, I know that the third side needs to be between 2 and 8 units in length. And if I'm going to refer to my third side as x, right, side length as x needs to be greater than 2, but less than 8. So that might be another way it gets sort of shown out here, okay? I need to break this down a little bit differently because I'm not thrilled really with the way that I kind of showed it to you here. So let's kind of get this out of the way and re-show you the theorem, and maybe we can talk through it, actually prove it, and realize this is more than just that third side being greater than the length of the 2 other sides, because that third side, right, the one that you wouldn't know in the premise of the problem, also that plus the smallest side, for instance, would still have to be smaller than the third remaining, or sorry, larger than the third remaining side as well. So the third side, we don't know if the third side's the largest side or the smallest side or the in-between side. So there's actually more than meets the eye here in this actual theorem, okay? So let's talk about this. Let's go ahead and introduce this one very gently right here. We're given any triangle. So notice here, given any triangle ABC, we're going to prove a few things here, actually. First of all, right, if we read this theorem literally here, the sum of the lengths of any 2 sides of a triangle is greater than the length of the third side. Question, how many sides are there in a triangle? Well, of course, there are 3 sides in a triangle. So if the way this is written, right, the sum of the lengths of any 2 sides of a triangle, that means let's pick any 2 sides randomly right here. So given any triangle at all, let's pick 2 of the sides randomly. So let's get, okay, let's pick AB and let's pick BC. Those 2 sides, when added together, would have to be larger than AC. So AB, length AB, and length BC added together got to be larger than AC. And does that look true based on this diagram? Does that look true? Does AB plus BC look larger than AC? Yes, obviously. It obviously does look bigger here, okay? Because these 2 points, let's read the theorem again, the sum of any 2 sides, and we picked those 2, larger than this third side. Yes, it's true. In fact, we can very visually see AB is the largest side in this triangle, this randomly drawn scalene triangle. And AB is the largest. So AB plus BC certainly can be larger than AC. So because AB is larger than AC, so this would actually be a property of proportions here. AB is larger than AC by itself. So AB plus BC, we would know from a property of inequalities, that this is a true statement, okay? What did our theorem say? So is our theorem proved all of a sudden? No, it's not. Because we just chose these 2 sides at random, that means we need to choose any of the combinations of the other 2 sides here. So why don't we choose, instead of talking about AB, well, let's talk about AB still. Let's talk about AB and then the smallest side here, AB plus AC. Would we know that that's greater than BC? Well, we can clearly show, right? There's at most one largest side of the triangle. So here, AB looks like it's the largest. Even if it were the same size as BC, though, we could still make the conclusion that AB plus AC was larger than BC, right? Because even if these equaled the same amount, what do we know about AC, right? Is AC a positive or negative number? Length AC is positive, so if we're taking a big number, adding a positive to it, it's going to be bigger than a number that was either the same size as AB or smaller than AB over here. Okay, so this one proven just by talking about it with you guys here. Okay, so what combination of the 2 sides haven't we looked at the sum of their lengths of yet? So we've looked at AB in 2 of them, so we're not talking about AB anymore. We got to do what? we got to do AC. We got to do the smallest side plus the medium side. And this is really the tricky one here. This is the really tricky one here. We already did this one here. We already talked about this. If AB is the longest in the first two statements, immediately proven. Why? Right? A property of inequalities, right? Property of inequalities. Because AB is the longest side. So in a triangle, you have at most one longest side, or that side also is the same as another longest side. So what I'm trying to show you here is that we're actually only going to have to prove this for the very bottom instance here. You're only going to have one longest side, so there's really only one side where you're going to run into maybe difficulty in proving this, because if you add the two smallest sides together, is it actually going to be bigger than the longest side? And AB is clearly the longest side here. So AB greater than AC because, well, AB is greater than AC. We see that there. It's kind of given to us, where we're given that this is at least the size of AC. So at least the size of AC plus another positive value is going to be larger than this side right here. Same thing for the second one, which I talked about. Third one, this is the one that we're going to need to prove. This instance, only statement number 3 is the thing we're going to have to prove here. And we'll get to that on the very next slide. Scattering and jumping on in. Let's go ahead and prove this one, guys. What's this one called again? The what inequality theorem? That's right, my friends, the triangle inequality theorem. Let's go into it. 2 things I'm going to put down right now. So you know what? We've proved those first 2 things right there, 1 and 2. We got to get to number 3 here. I'm putting down our whole rationale, which I just talked about with you guys here, is that we start, right? We start this proof. We don't have to put our given down, right? Because we're just given this triangle and the triangle's pictured here. We don't, just saying triangle ABC doesn't tell us anything. So we don't start with givens. We'll start with number 1 by making an assumption, right? We assume that one of these sides, doesn't even really matter about how we drew it to, but just assume one of these sides is longer, is the longest side, or it's the same, right? Or it's the same as another side. It's just as long as another long side, for instance here. So here we're going to assume that segment AB is the longest side. Therefore, right, AB would be at least the size, the length of BC, right? It's likely in the diagram bigger, right? Greater than, but I put greater than or equal to because we can assume that that 2 sides are as long as one another, or 3 sides, right? This should work for an equilateral triangle as well. In a triangle, there's going to be at most one side that's larger than either of the sides. So I think I said earlier there was at most one largest side. What I meant is there's at most one side that's larger than the others. So we're giving that to AB, which we leave open the possibility that AB is the same length as either of the other 2 sides. But if there's one that's, if to say this is a scaling triangle, let's just assign AB to represent the one that we care about really in terms of proving this, because is the sum of the small sides, does it have to be larger than the largest side here? Okay, and then through a property of inequalities, we can prove statement number 2 and statement number 3, because we know AB is larger than AC, AB is greater than BC, so we can add these 2 here, right? Add these 2 sides together, larger than the third side. Add these 2 sides here, larger than the other small side as well, okay? So what we need to do is jump into and prove this, okay? What we're going to do is prove this in this one, and this is going to involve a bit about those theorems we did last lesson. Yes. That's my hint there. That's really my hint there. And I bet you'd have trouble proving this one so without my help. So what I'm actually going to do is direct your attention to step 3 and just sort of tell you what you got to do next, because these are pesky, right? These proofs exist for a reason. Like they're hard to prove on your own, but you got to know the actual theorems of them so that you know how to do the math problems. But step 3 is going to be involved drawing an auxiliary set, which can always be tricky to kind of remember or figure out what's the right auxiliary set to draw in. So I'm just going to kind of give this one to you. This is what we're drawing in for step 3. We're not changing the triangle exactly, but what did we just create? We just dropped in a perpendicular. So obviously you know what this is by now, right? Through a point outside a line. So through point C, through vertex C right here, we dropped in. Through that point, we dropped a perpendicular to this other line here, to line AB. Okay, so a very useful auxiliary set theorem that we're doing through a point outside a line, exactly one perpendicular to that line can be drawn. So we've drawn line CZ through Z such that it's perpendicular to AB. All that's totally valid. But the big thing that I was saying a minute or 2 ago was that we've created, by dropping this perpendicular, what have we created? Well, we had this original triangle, right? That's what we started with. Now what do we have? We have a triangle here, And we have a triangle here. Okay, so this right triangle here and this right triangle here. Interesting. The idea that in this problem isn't that they are right triangles necessarily, but the idea that's important is, ooh, I dropped a perpendicular. Interesting, okay? And my goal is I want to prove that AB has to be smaller than the sum of AC and BC. So I'm highlighting that because perhaps something jumps out to you. AB here needs to be smaller. So this plus this we need to prove that this plus this is less distance, is not as long as this plus this, right? Because AB is the same thing as AZ plus ZB from the segment addition postulate, okay? What are you noticing? What are you noticing? Okay, hold that thought for a second. Hold that thought. Because I'm actually, in case you didn't notice it here, I'm going to highlight this a little bit. Let's check this out here. I drew that first. Ooh, and I'm putting that in. That is my big assertion here. Is, you know what? Let's look about this part of the longest side. Let's look at that part and compare it to this shortest side of the triangle right here. And I'm making this conclusion. What allows me to make this conclusion that AZ has to be shorter than AC? Length of AZ's got to be shorter than AC. Well, line CZ right here. Line CZ is right here, and point A is up here. Okay? What's significant about this line segment to line CZ? Well, line AZ is the what? Is the perpendicular, and segment AZ is the perpendicular segment to line CZ. So we know that AZ is the shortest segment that can be drawn from point A to line CZ, and any other lines on top of that, right, that go from point A to line CZ, 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 they're all going to be longer than this. This is called the first minimum distance, right? This is the minimum. In another textbook, I like the name of the theorem. It's called the first minimum theorem here. But instead of your textbook, they just call it a corollary from the triangle inequality. Okay? This angle here is a right angle, and so opposite it is going to be the longest side, right? A 90-degree angle is going to be the largest angle in a triangle, so the largest angle is opposite the largest side. So here's kind of where we prove, right, talking about informally proving the hypotenuse of a right triangle is larger than any other sides and larger than either of the legs, okay? Not the sum of the legs. The sum of the legs still need to be larger than the hypotenuse, but anyways, I think you get what I'm saying here. Okie dokie, AZ, right, length AZ, right, we're not anything above there, we're talking about length. Length AZ is the shortest distance from A to CZ. And we know that because it's the perpendicular segment from a point to a line, and that is the shortest segment to that line. Okay. Likewise, all right. So notice here, this is, again, we wanted to get AB is less than the sum of AC plus BC. So we need to talk about BC right now. What can we say about BC? Well, BC is got to be larger than BZ because, again, from point B to line CZ, this is the perpendicular segment here. And this perpendicular segment is shorter, is smaller, is less than the length of this segment BC. Segment BC is larger than segment or longer than segment BZ for the same reason, because the perpendicular segment is the shortest segment we draw from point B to line CZ. Okay, so what do we notice here, right? What do we notice here? Well, we got a small part. If we added a small part to a small part, and then we added a large part to another large part, right? Larger by comparison, relatively large, right? We add this thing, which is bigger than that thing, and this thing, which is bigger than that thing. We add those together, and then we add the two smaller things together, corresponding parts here, and these guys here. What's going to happen? Well, this plus this is going to be greater than that plus that. And that's great because we have AC, boom, plus BC, boom, right there, is part of what we're trying to prove. And we're just trying to show it's greater than AB. So guys, when we add these parts together, we're going to get pretty close to proving this here. So first thing we need to do, step 4, is to elaborate a little bit here. AZ is the shortest distance from A to CZ. So what we need to say here is that AZ is less than AC, right? Or AC is greater than AZ because AC is not the perpendicular segment, right? AC is not the perpendicular segment to CZ. Also, we need to say, we get into our proof here that BZ is shorter than BC, okay, than BC right here. And that's just from step 4. So now what we need to do, we need to start making it look kind of like this. We need to take AC, and what do we need to do to it? We take AC and add BC to it. So those are the two larger expressions here, and they're both greater than AZ plus BZ. So let's do that. Let's write that all out here. We'll kind of just do this addition property of inequalities, and we just need to say a property of inequalities here, right? AC plus BC, they're both greater than, so they got to be greater than AZ plus BZ as we add sides of the expression together, okay? Are we there? Can we get there to the last step? Technically, this last step would be 2 steps because instead of writing AZ plus BC, what do we want to write, right? We can figure out what we need to replace AZ plus BC with. Well, we have AC plus BC here on the greater than side, kind of, right? This side is greater than that side, so that's good. AC plus BC is greater than something here, and it's greater than this left side here. How can I replace then AZ plus BZ with AB, right, and finish our proof here? Well, AZ plus ZB, or BZ, equals AB by the segment addition postulate, okay? So I could have written out as additional step. I didn't for step 7, but I do reference the segment addition postulate in step 7. So what did I do? I combined steps. So my last step is segment addition postulate and substitution here, okay? So AZ plus BZ equals AB by the segment addition postulate. So I can take this right here, right? I can take AZ plus BZ and replace it with AB, and that would be substitution as the second part, okay? So 2 reasons gets us there. We've finally proven the third thing, and we proved the first 2 things earlier, right? The larger side, or the one that's tied for longest side, we add another side to it, still going to be larger than the remaining side we haven't talked about yet. And the only one that we really had to do all this work here, all this triangle inequality work with, was really the situation where the largest side, how do we get to prove that the 2 shorter sides added together are still longer than the largest side here, okay? So 3 inequalities. You do get 3 inequalities with this, which was the reason why word problems can get a little bit tricky here. A triangle has a side length of 2, 6, and x. Find the range of possible values of x here, okay, of x here. So quick hints on this one here. When it says range of possible values of x, what they usually mean there is that x is going to be between something. Okay, going to be between something. So if you're paying attention earlier when I went through this kind of example, even before we talked about the proof and talked about the theorem, our answer looks kind of like this. The third side needed to be a certain length and needed to be under a certain length here, okay? So the size of the sides of a triangle are reliant on the other 2 sides, right? And we need a minimum size, right? A minimum size to create a triangle with 2 and 6, and maybe you have an idea what that is. And there's a maximum size that could possibly exist for the third side, right? For sides of 2 and 6 here, okay? So the way you could do a problem like this is you could just set up 3 inequalities, for instance, here, right? Assign this one here. Let's the segment with a length of 2 equal AB. Let the segment with of length 6 be side BC, for instance, or the length of BC here, and you can let x be AC here, okay? So we wanted to get our answer, and we'll put our answer up here so we see our answer in a second, but AC needs to be a certain amount of distance, right? Certain amount of distance to make sure we can create a very, very narrow triangle with a side length of 2 and side length of 6. We can figure that one out. And it could be pretty big. Like if AC is the largest side of the triangle, it might be a lot bigger than that, okay? So what you can do to solve a problem like this, you can go through these 3 things right here, test these 3 inequalities, and get your answer, right? Get your answer, because we don't know if AC is the largest side or not, right? Largest side or not, okay? AB, what's AB? AB is 2, and BC is 6. So that means the first thing that we can say about AC, and AC is just x, right? AC is x. The first thing we can say about x is that x needs to be less than 8. Okay, x needs to be less than 8 here. Let's test this one right now. So let's test situation number 2. So this was situation number 1. Let's test situation number 2. And this is going to be AB is 2, AC is x, and if we take the 2 and we added x to it, it's got to be larger than this pretty big side, right? Compared to 2, pretty big here. Got to be bigger than that, okay? So now, right, if AB plus BC, plus AC is greater than BC here, to figure out what AC, the length of AC must be at a minimum, right? At a minimum, what do I have to do to both sides? I have to subtract 2 from both sides, so I get x is greater than 4. Okay, x is greater than 4. There's another piece of criteria right there, right? Another piece of criteria right there. X has got to be greater than 4. Okay, criteria number 3, or at least another way we can look at this thing here is that AC is also one of the smaller sides, but perhaps BC is another one of the smaller sides here. So this might be, if it's smaller than 4, right? If it's smaller than 4, we're gonna, or sorry, if it's smaller than 4. No, if it's bigger than 4, higher than 4, we would take that, and I'll talk about that a little bit later. But anyways, AC, and AC again, sorry, AC we said was going to be X. Situation number 3 right here. That's what I'm doing. 3. X plus, and BC is 6. Is that greater than AB? AB is 2. And here I know my answer, right? Here I know my answer because you know what do we know about 6? 6 is already greater than 2, so we're not going to care about this one. This one here is not going to tell us any information about what X is, so we just need to take what we learned here and what we learned here and bring it together to find a range of possible values here, okay? So situation number 2 is telling us that X needs to be greater than 4, okay? So 4 is something called my lower bound, the lowest, the smallest that X, that side length, could approach at least, could approach. So X actually can't be 4. The segment length couldn't be 4 because then if you connected a segment of 2 and a segment of 4, that length total would be 6, right? It would be a line segment. It wouldn't actually be a triangle. So anyways, 4, notice here, there is no equal to here. It's 4 is less than X, which is less than 8. We get 8 over here. Okay, and there we've arrived at our answer here. 4 is less than X, is less than 8 is the range of possible values, range of possible values. Okay, so you're always going to have a lowest that it could possibly approach and a highest that it could be approaching. And you can really reason through this in your head. You can get to it pretty quickly. Now, yes, I will talk about a shortcut in a second. Don't worry. If you notice the shortcut, I'll get to it. But if we had a length, a triangle with a length of 2, and then another side, right, which is just maybe pointed a little bit up, so it goes to a third non-collinear point here. That's a length of, well, if this is 2, this is probably about 6 so far. Then the third side, right, if it's making a triangle, it's just above all this, right? This would still need the criteria. This would have to be less than 8. Okay, so 8 units would get us from 2 plus 6, but here this wouldn't be 2 plus 6; it'd be less than that because this would have to be tilted this way, so it's not a line segment. Okay, so less than 8. If we do it like I showed you before, right? If this were 2 right here, and the second side were 6, right? Basically, we'd go over the 2 again, but a little bit above, and then go on 4 more, right? So this here is 6. The third and remaining side, okay, third and remaining side would have to be greater than 4, right? Greater than 4. So that's how you can kind of think about it here. How can we look at these numbers? How can we get this, right? In situations like this, you want to be able to solve this very quickly. Tell me, how are we going to get X here? Well, your lowest, okay, your lowest here, let's say that this is A, this is B, and this is C. Okay, maybe we'll just leave it as X. This is A, this is B, and this is X right here. The lowest amount, how do we get the lowest amount? What would we have to do? Okay, we'd have to take the absolute value of A minus B. Okay, the absolute value of the difference would be our lowest in the range of values here. Okay, so 2 minus 6 is -4. Obviously, a length can't be negative, so that means the minimum size of that third side needs to be at least 4, all the way up until what? The absolute value of, well, 8 is what we got earlier, and what do we notice? 2 plus 6 equals 8, so it must be the absolute value of A plus B, A plus B. So this here is the direct formula, right? This here actually is a direct formula that will you can use, which is more simple maybe than trying these 3 inequalities on their own and then turning it into a range of possible values. So perhaps you just use this in the future, and this will also come up in the problem set, so you kind of get it a little bit later. Okie dokie, ready, set, go. You guys did it. You guys figured it out. It's all good. So, hey, just wrapping this up here. Quick question. Who's going to tell me the fastest? Who's going to tell me the fastest? Inequalities for one triangle. The length of two sides of one triangle are 3 and 5. The length of the third side must be greater than 2. I know, you know, guys, because I explained it so well, right? So well. Must be greater than 2, but less than 8. Okay, greater than 2, right? 3 plus, or 5 minus 2 is, 5 minus 3 is the 2, and 5 plus 3 is the 8. And they're positive numbers, so don't have to worry about thinking about absolute value there. So got the answers, boom and boom. Not too hard, but now hopefully you understand why and you have it proven. Okie dokie, so I said the second half of class was a bit of a review for the stuff we did last time. Hey, fun problems coming up. Review time, we're going to be reviewing some of the questions related to this theorem from last class, okay? So here you have to change your thinking a little bit, which is why I'm giving you a bit of a heads up here. In last class, we had this theorem. If one angle of a triangle is larger than a second angle, then the side opposite the larger angle is larger than the side opposite the shorter angle. Okay, makes sense. And you can think about this in terms of 3 angles within a single triangle, right? Within a single triangle, 3 angles. They're all different sizes. The larger angle is going to be opposite the longer side, for instance. And the larger side is opposite the largest angle of the 3, okay? That being said, let's go ahead and jump into it here. If the angles have the indicated measures, what segment is the shortest in this entire diagram? To give you guys like about a minute and a half to see if you can figure out this on your own, because I think you can do it. But these are tricky problems for people, so maybe you have to wait for my explanation a bit later. I have this down here actually. My recommendation to you guys, and when I go over it, I'll say this too. My recommendation is stay organized as you try this one. Stay organized. Okay, so what is the shortest segment in this entire diagram? Not what's the shortest in this triangle and what's the shortest in this triangle, but what's the shortest segment in the whole thing, right? So we have 1, 2, 3, 4, 5 segments. This one's shared between the 2 triangles. What's the shortest of the 5? Ready, set, go. Minute and a half on the clock. You got this. All right, minute to go. All right, here's my recommendation, guys. Here's what, stay organized, right? So remember this theorem here, right? This section is about inequalities in one triangle, one single triangle. So the only reason why you're seeing this is because this triangle shares this side with this triangle. So you got to look at both these triangles individually. 40 seconds, that's my hint, 40 seconds. And then you got to make a comparison. You got to make a judgment using properties of inequalities. 20 seconds. All right, do you have QRS ranked? You still have 12 seconds. Do you have QRS set up? Here, this is QRS right here. What's the longest side in QRS? What's the longest side in QRS? 5 seconds. 4, 3, 2, and 1. Okay, so you know what? I'm going to pick up right where I was kind of leading you, guiding you guys here. In a problem like this, you want to stay organized. You certainly want to stay organized, okay? So you're comparing, right? We only can make conclusions about this triangle and then conclusions about this triangle, but the problem's asking us for what the shortest is in the entire diagram. So I guess what that means is we need to look at this triangle first and look at this triangle and see, is there a conclusion we can make? Right? Is there something we can do? So anyways, gather as much information as possible. I was recommending doing this one, triangle QRS, just because I noticed 2 greater than symbols. So maybe this one might be a little more straightforward. I don't know. There's only 1 greater than symbol there. Anyways, triangle QRS. I asked you, what's the longest side in this triangle? Well, this is a 77-degree angle. So we'll look to the largest angle opposite the largest angle is going to be the largest side. So we know that SR is the longest distance. That's not going to be the shortest side out of all this whole diagram here. Neither will SQ be, huh? Right? Because 52 is the next one we'd look at, right? That's somewhere in between. So SQ is the second largest side in this triangle here. That means that QR is the shortest side in this triangle here. So length QR, right? Length QR is what we write here for the shortest side. Let's look at this here, because you know what the really tricky thing is? These three angles here are actually all larger than angle P. Actually all larger than angle P. And this is the problem, right? Think about where people get screwed up on problems like this before, and why teachers ask them, and why teachers ask you to think critically and work through things and apply things, rather than just what comes to your mind first. Because if you had said, maybe looked at this answer to this problem and answered it based on what's opposite the smallest angle, you might have said that that was the smallest side. But no, this isn't the smallest side because it's the middle length, right? It's the middle length of the this triangle over here. So even though this is 40 degrees, that's the smallest degree measurement out of all the the 6 angles that we have. This side here, it's definitely the smallest, right? SQ is definitely the smallest in triangle PSQ, but you know what? It's bigger than QR in triangle SQR here. So this part doesn't really matter up here, but this is isosceles we haven't noticed. So we could say, if we wanted to say super organized, we know that PQ is larger than SQ because 70 degrees is larger than 40 degrees. So PQ is one of the 2 largest sides here of this triangle. And PS is the other one here. Okay, so by sort of ranking each triangle, we ranked this triangle, and then we ranked this triangle in terms of largest, smallest. What do we notice? We notice this here, SQ appears in both of them. And is it the smallest in both triangles? No, there's one triangle smaller, QR, so that means QR is the smallest segment in both triangles. Does that make sense? People have trouble kind of with problems like these, so maybe I might re-explain this or show it to you a little bit differently. So let's look at it one more time and pretend like you're just doing it again. But here, look, laying it out here. The 2 biggest in this triangle, PS and PQ, because this is isosceles and these are both greater than 60 degrees, right? So it's going to be larger than whatever the vertex angle is. So QS, smallest in this triangle, but QS, second smallest in that triangle right here. So because we know this, right, using properties of inequality here, right, we're going to compare this thing to, we know that PS, for instance, is greater than QR because PS is greater than QS and QS is greater than QR. So by transitive property of inequalities, right, PS greater than QS and QS is greater than QR. Therefore, we can conclude that PS is also greater than QR. And PQ, because it's greater than QS and QS is greater than QR, by a property of inequalities, we know that PQ is greater than QR. So that means we know that this side, and this side of this triangle are still larger than this side of this triangle over here. Okay, does this make sense? Right? Some triangles are larger triangles, other triangles are smaller triangles. So if you have a shared side, it might not be the one across the smallest angle out of all the triangles. It just might be in the smaller triangle here. Okay, and the reason why, really, the thing that we're able to prove it here is that we have a common link between triangles, right? QS appeared in that triangle. It also appeared in that triangle here. The common link, and we'll sort of relatively show where everything's laid out, and then we just got to say, hey, this has got to be the smallest out of all of them. Okay, does that make sense? QS is the one that really allowed us to make this conclusion that PS could also be larger than QR, and PQ could be larger than QR. So therefore, we've proven that segment QR must be the shortest segment. Okay, that makes sense. If you're just like, that wasn't that hard, I got that, I'm going to give you a harder diagram. Boom. There you go. Booyah. We actually have not one, not even just 2, but 3 sides shared between multiple triangles here. Okay, so question, if the angles have the indicated measures, what segment is shortest in the entire diagram? I'll leave you about 2 minutes. Oops. Ready, set. I don't have the ready, set, go diagram, but anyways, ready, set, go. See if we can figure it out. Ready, set, go. I'm going to put that up there. Yeah, boom. Stay organized, guys. Stay organized. All right, we got 1, 2, 3, 4 triangles. Rank them out and see what you can get. See if you can beat me to it. You guys got 1 minute and 15 seconds. We'll go over it. Get on with our merry way. I think it's homework after this. These are pretty classic geometry problems. Right, pretty tricky stuff. People always have trouble with this. That's why it's worth practicing. But pretty fun brain teasers when you start getting better at seeing things. It's more than what meets the eye. Stay organized. Stay organized. Triangle ABM. Yeah, did you get what I got? Triangle ABM. That, BM, so this is M's right here. BM has got to be the smallest, is across 25-degree angle. And then finally, AM is the next largest. And finally, AB. Oof, yeah, AB, 120 degrees. That's a big angle. So this is the largest side of the triangle there. Okay, so question is BM, right? BM right here. It's in this triangle too. Is this going to be the smallest side? Smallest side. Well, it's actually the smallest side of this triangle, right? Because this is isosceles and isosceles right triangle. So you know what? Actually, MC equals BM. So maybe MC and BM are both the smallest sides. I don't know. 35 seconds. See if you can beat me to it. And then if you do finish this in the next 30 seconds, you're in A-okay. You're doing great. You're in great shape. Keep on going. All right, give you 20 seconds of peace and quiet, and then we'll go over it. 5 seconds. 3, 2, and 1. All right, I want to continue with showing what I said about BMC. BM equals CM because I saw this right triangle. BC is the largest because it's opposite the right angle, right? The right angle. This would be the minimum distance from C to line BM. So this is longer. Triangle CDM is what we're going to look at next. We looked at the 58-degree angle, so that's the smallest in this triangle here. So CD is the smallest in this one, and this is also isosceles, so DM equals CM here. Okay, so I know that CM actually, now I know that CM isn't the smallest either. So I knew that BM wasn't the smallest because BM equals CM. Well, they equal each other, right? They equal each other. So maybe both of them were the smallest. All right, so even though BM and CM equal each other, and it looks like either could be the smallest, you know what? We know that CM is larger than DC. So since CM is larger than DC, DC might be, or CD here, right? The smallest in this triangle, still larger than the smallest in this triangle. And also larger than the smallest in this triangle because BM equals CM, right? And CM is larger than CD, okay? So looking like maybe CD is the answer here. Let's look at the last one here. We got EM greater than DE, and DE equals DM. So again, we got isosceles triangles. Our problem was a lot easier, actually, because we had isosceles triangles. And you know what? Here, the 42 degrees, we can look at maybe DM right here. DM, how does it compare to CD, which was the smallest one in the last triangle? Well, DM was larger than CD here. So our answer, boom, using properties of inequalities to combine all information. What is our answer here? Did you get the right answer? Is it CD? Yes, yes, it is CD right here. So you got to look at where the smallest ones are. And so first of all, right, you could have just arranged each one. That's one way people do this. They don't just like kind of go through and talk through it the way that I did. So I would recommend just going through all of them. Like for instance, triangle EDM and saying, you know what, EM is greater than ED, which equals DM, right? It takes 2 seconds to do that. And then you can say DM equals CM, which is greater than CD. Takes 2 seconds to do that. You see what I'm saying? And then you can do that one and that one, 2 seconds and 2 seconds. And then in 8 seconds, you have all this information. And here, this is where you're going to kind of start noticing where there's overlap, okay? These things all equal each other. BM is the smallest here. BM equals CM. But you know what? CM also equals this CM down here. There's overlap here. So this proves that BM and CM are larger than CD, larger than CD. So we're kind of stringing it together by transitivity, right? BM and CM are larger than CD. In this one here, what's the common thread in this one right here? Well, we know that MD is also in this triangle right here. And this equals CM. This equals CM here. So MD equal. So in fact, we actually have 3 segments that all have the same length. I never really noticed that one before. MD would have to be the same length because it's an isosceles triangle here with CM. And MB has the same length as DM because it's in an isosceles triangle also with CM being the other leg here, okay? So here we have the some of the shortest sides here. MD, right, DM, CM and BM, and they're all larger than CD. So that proves to us that CD is the shortest segment. CD is shortest. All right, these are really good problems for balancing a lot of information and making an argument. Even though if you don't have to say that argument out loud, you still know how to make the argument. You would know how to make the argument by being able to deduce the correct answer here. So even though something like this, because I've done this a bunch, isn't very hard for me, it might be hard the first time going through, and it's fun to get better at these. So probably need to do problems like this when we practice in Zoom sessions. Okie dokie, that's that. I think you got some problems kind of like that in the homework tonight. Don't forget, triangle inequality theorem. Add the 2 sides you know together. That's the upper bound. That's the highest in the range of values for the third side. Subtract 1 from the other, the absolute value of that. That's going to be the lowest bound, right? Lower bounds for the range of values that a third side could possibly be. Okay, so there's triangle inequality theorem. And finally, just a whole bunch of practice there with those multiple triangles using one inequality triangle theorems within triangles that share sides. All right, folks, I hope you get some good practice here. We got some challenge problems, it looks like. Take care. I will talk to you guys later. Bye. You can hardly stand it though. Right now you know it's not going to stop. It's not going to stop. It's not going to stop till you answer.
F minus. What? Did you say S?